Hello, good morning, everybody. I hope you can hear me well.
Yes.
Good. Welcome to the instrument science session. Yesterday we had already a first block of this session. Today we will have two blocks. The first one right now until 12:30, more or less, and the second and final block at 3 o'clock in the afternoon. Today, as yesterday, the agenda is quite packed, so I would like to start as soon as possible. The first speaker in the agenda is Walid. Walid, are you there?
Yes, can you hear me?
Yes, very well.
Okay.
Can you share your desktop? Okay, we see your slides. You can start whenever you want.
Okay.
Please keep in mind, you and the other speakers, that try to stay within 15 minutes so that we will leave 5 minutes at the end of the talk for questions and answers.
Okay.
Thank you.
Thanks. So I'm going to talk about higher order Hermite-Gauss modes and the possibility to use them in gravitational wave detection. And this work, we've been conducted this work for several years now. So let me recall the problem of mirror thermal noise. So mirror thermal noise is the distortions of the reflective surface of a mirror due to its non-zero temperature. And these fluctuations, these distortions are interpreted as the mirror displacement given by the pointer, maybe. Yeah, given by this integral, the overlap of the intensity of the modes by the distortion of the mirror. So one can easily understand that if we use larger modes, the averaging here will be bigger, so this integral will be smaller. So if you use, for example, flat top modes, that will be very interesting, except that these kind of modes require aspherical mirrors. Higher order modes, on the other hand, have reduction factors which are quite interesting. They have a better averaging of this integral, but they also need they need spherical mirrors, standard spherical mirrors, except that they are a little bigger. So they are quite interesting modes in this sense. So higher order modes, propagation modes, with respect to the fundamental modes, are larger and more divergent. And they also have a degree phase which vary more than the fundamental mode. So if we see what happened inside a cavity, they will have resonant frequency nu, which depends on the total order of the mode. So if we take modes with different total orders, in general they will be non-degenerate. But if they have the same total order, they will of course degenerate. So for example, if we take Hermite-Gaussian modes, the HG55, for example, it will be degenerate with 10 other modes since the total order is equal to 10. Axisymmetric Lagarde-Gauss modes are also another base. So if you consider the LG33, for example, it will be degenerate with 9 other modes represented here. And these LG33 modes were generated and studied by several groups now. And what was very interesting, it was that it was injected into the Glasgow 10-meter interferometer. And we see here that the mode inside the cavity is completely distorted. These images are taken from this reference. So this effect is due to the coupling between degenerate modes due to the imperfections of the mirror surface. So what I'm going to show is that HG mods are immune to this phenomena called the pseudo-degeneracy. And this is the outline of my presentation. So first of all, I will talk about this immunity of the HG mods. Then I will show how we generate these kind of mods and how we measure their purity. So let's start with the first point. So first of all, we consider a mirror which has a map with some imperfections generated by the software Oscar, which follow this PSD as which follows the law 1 over kappa to 2.3 with an RMS value of 0.5 nanometer. Kappa here is the spatial frequency, and this is the law governing the real mirror of advanced field. So the coupling between AG55 modes and degenerate mode indexed here by the value Q is given by this integral. And now if you look into this product of modes, it evolves as follows. So when we increase Q, the area in which the overlap of the two is non-zero becomes more and more restricted. And if you look at the 2D Fourier transform of this product, we see that the imperfection Z will need frequencies more and more high as far as we increase the index Q. So when we put some numbers on this, we see that most of the coupling is done between the HG55 and the adjacent modes Q equal plus or minus 1. So it means HG46 and HG64. And this is the dominant coupling. So in the following, we get only interested in this coupling, the coupling to these adjacent modes. So let's see what kind of imperfections are responsible for this coupling. So for that, we use the Zernicke polynomials, which are a base. Each polynomial here is indexed by two integer n and m. N is the radial index, and m is the azimuthal one, and we have this condition. So we can decompose the mirror shape on this polynomial, and with n equal 20, we are able to have a recomposition with an error smaller than 1%. And we get interested in the coupling of each polynomial, the coupling between HG55 and HG46 due to each polynomial with this effect. So if we look at we take symmetry consideration, we'll see that for n equal to 0, this integral is equal to 0. And this is also the case for n when n is odd. This simplified positive. Let's see, for example, now the first order astigmatism, n equal 2 and m equal plus or minus 2. And we look at the symmetries here between the product and the Zernicke polynomial. And we see that with symmetry, the coupling will be different from 0. But if we take the other polynomial, astigmatism polynomial, for symmetry reason, we'll always see that it's equal to 0. And we can go further with this consideration, and we show that when m is higher than 0, the coupling is also vanishing. Now, if we take n higher than 2 and sorry, if we take the polynomial z4 minus 4, we see that this polynomial is antisymmetric between with respect to this line, and for this product, it's not symmetric but almost. This is maybe is well seen when we look at the polar diagram. We'll see that this line here is this 45 degrees here. This polynomial is anti-symmetric. This one is slightly symmetric, but not perfectly. In any case, when we look at the coupling, the coupling with this polynomial will be negligible, and this will always be the case. It will also be the case when we take m higher than 4, because when m higher than 4, it means that we need n higher than 4, and here we need higher frequencies of the mirror imperfections. So also this can be neglected. So to sum up, the coupling between HG55 and the adjacent mode is dominated by the generalized astigmatism m equal plus or minus 2. In particular, there is a linear combination of the Zernicke polynomial zeta plus 2 and zeta minus 2, which simplifies a lot of the coupling between HG55 and the adjacent mode. It can be written this way. And here, with symmetry consideration, as we can see on this, comparing these images, gamma 1 theta 2 is equal to 0. And theta here is the angle of the mirror. So it can be chosen so to cancel this factor and at the end cancel the whole coupling, at least the main contribution to the coupling between HG55 and the adjacent. So a priori, angling the mirror around the optical axis can cancel the coupling and then the pseudo-degeneracy. So let's put some numbers on this. When we use the Zernicke polynomials formalism, we see that when we increase the considered n, we converge toward a value which is 27.5 degrees for the mirror we considered. And we see here, obviously, that considering the first order astigmatism is not sufficient. We conducted also a darker simulation on a Virgo-like cavity, and we measure the coupling efficiency of the mud into the cavity, and we see that by turning the mirror by 29 degrees, we recover a nice mud with 99% of coupling efficiency. So, which is in agreement with the other formalism. We applied also this with the 1010 mud, and the coupling efficiency increased from 62% to 96%. And also, if we look at the coupling between the mud, we see that by turning the mirror by angling the mirror by 29 degrees, we decreased by more than 2 orders of magnitude the value of the coupling. Okay, so let's see now how we generate HG modes. So nothing new under the sun.
2-3 minutes left, Walid.
How many?
3 minutes approximately.
I talked between 15. Okay.
Yeah.
Okay. So the generation is we use SLM spice light modulator, on which we send a Gaussian mode, and then we look at the Fraunhofer diffraction in the Fourier plane, the image plane of the Fourier lens. So the difficulty here is to calculate the phase map we have to send the SLM. For this, we use an iterative algorithm which generates in a restricted area the mode. And then we add a blazed grating to displace the mode. Because we want to avoid all non-diffracted light, which he usually concentrated in the middle. So the efficiency here is around the theoretical efficiency around 20 to 40%. And this is the experiment. We have the laser. We filter it with a single mode fiber, and then we use the SLM and an iris to get rid of non-diffractive light. This is how the mod looks like. And then we clean it using a modeling cleaner cavity. Then we send it to the diagnosis cavity. I will talk about that. So this is the mod we obtained before and after the mod cleaner cavity, with the efficiency which is quite low, but there is a scope to increase that. And we can also create very high order mods like the HG2525 and even have fun by creating any mods and transforming them into axis symmetry. Lagrange. So for the purity measurements, we used a triangular cavity. Why triangular cavity? Because inside the triangle, the degeneracy between these modes is simply lifted. The modes which have the same symmetries are simply thrown away by half a free spectral range. And the modes with the same symmetry, they are pushed away also due to the astigmatism, due to the incidence angle here on the end mirror of the cavity. So when we measure the coupling efficiency, which is a lower limit to the purity of the mod, we obtain 96% for the 5.5, 93% for the 10.10, and 78% for the HG1550. And when we look at the output mod of this diagnostic cavity, it's basically not changed. It keeps qualitatively it's the same. Okay, so to conclude, we generated HG mods of arbitrary order, and there is no fundamental limit how high this order can reach. Low efficiency, that's for sure, but there is we think that we can increase that up to 30%, but they are of high purity. The immunity of HG mods to pseudo-degeneracy still needs to be experimentally demonstrated, although we had to use this effect on the mod cleaner cavity. We had to angle mirrors to obtain these pure mods. And we'll intend in the future to use this technique with high power lasers in order to see how high we can reach, how high power we can reach with these. Thank you for your attention.
Thank you, Walid. We have time for.
I was late, or?
No, it was fine. Just
fine.
1 or 2
Okay,
minutes. We have still time for 1 or 2 questions. Jan, please go ahead.
Yes, thank you. Thank you for this presentation. So, I mean, we had this. I think I'm not able to, for myself, draw a conclusion from this presentation. So I'm wondering about the degeneracy, what the requirements really are to be able to operate in interferometer with such a mode, because the criticism was always that we will not be able to operate the interferometer in a reasonable way when you have these degeneracies. But now it seems that you have like some idea that this is not really affecting us so much. The other thing is, what about point defects? They for sure will also lead to some the problem. Okay, here's what I got from the past. So whenever you have some perturbation in the optical system, be it some point defect or something like that, or something not optimal, then this would create essentially energy in modes that you don't want to have. So with respect to point effects, do you have an idea if that is a negligible effect, or is it something that you are still about to analyze in addition to what you have done so far? And then again, back to the question I asked, like, what are the real requirements that we have from the interferometer operation, like how well this has to work in the end?
Okay, I mean, there's a lot of questions. what do you call pointed effects?
Well, something which is so small that you don't describe it by the PSD. Typically, I mean, I think the PSDs don't capture at all the point effects, but okay.
Okay, I see what you mean. It's difficult to answer this question because, of course, with simulation we cannot. I mean, we didn't conduct any simulation with this kind of effect, and up to now we didn't see it, at least on our experimental layouts, any effect on this. So I think that more experimental work is required on bigger mirrors and see what are the technical limits. But up to now, we didn't see any effect like this.
Okay.
I don't
So
know
in any case, yeah, no, it's fine. And I don't know because I'm of course more used to the Laguerre-Gauss story, so yeah, it's for me a bit hard to understand. But yeah, okay. Anyway, I think that the point effects might be important, but okay.
Yeah, it's for sure something we have to investigate. But up to now, we didn't see anything.
Okay. Thank you. I think at this point we should proceed. Thank you again, Walid. And the next speaker is Samuel Rawlinson. He will speak about recycling cavities and telescopes design for Einstein telescope. Whenever you're ready, you can share your desktop and start your presentation.
Yep. Just share the screen here. Okay, so yeah, hello everyone, and yeah, as the title here implies, I'll be talking about our recent work on determining the feasibility of using beam expanders in the arms of the ET detectors. And just to note, you can find these slides and the associated paper at the DCC number given here. So the first thing I just want to discuss is the motivation as to why we'd want to have beam expansion telescopes in the arms of the interferometers in the first place. So there are multiple motivating reasons for this, but hopefully I'll encapsulate the main ones over the next couple of slides. So one of the major factors really is simply due to the larger beams that are at play in ET and in third generation detectors more broadly. So just naturally, the longer arm cavities that are present, so 10 kilometers for ET, just result in larger beams. But I should note as well that this is really a feature rather than being a bug, as obviously we want larger beams anyway to reduce coating thermal noise, especially for ETHF, where this will be a dominant noise source in around the 30 to 200 hertz frequency band. So you can see here the beam sizes on the cavity mirrors given for LF and HF. So this is why you see a pretty large beam size on the HF cavity mirrors. So just to compare this to advanced LIGO, by the way, this is just over double what advanced LIGO has got currently. So quite a significant increase on the current generation. And so if fairly obviously, if no beam expansion optics exist between the beam splitter and the ITMs, then the beam size on the beam splitter will be comparable to the beam size in the ITMs. So you effectively need a very large central beam splitter to avoid clipping losses. So just to give an example actually of that, from the 2020 design report update for ETHF, assuming you have a 60-degree opening angle on the beam splitter, you'd actually need a beam splitter with a diameter of greater than 120 centimeters to avoid clipping losses of greater than 1 part per million. And so beam splitter sizes of this magnitude are difficult to achieve, both in terms of cost and practicality. So reducing the beam size in the central interferometer would certainly help. So another factor to consider is that telescopes in the arms will allow for greater flexibility in terms of steering the beam. So in particular, this is important for ET, as ET consists of co-located detectors. So telescopes in the arms really offer the ability to steer the HF beam away from the suspension chain of the low frequency ICMs. And just to bring some of this together, so this is an example schematic of one of the corner stations of ET. So this has been shown on a few other talks in this symposium over the past few days. And yeah, so this basically shows the optics for both LF and HF in one corner station, with example configurations for the LF and HF telescopes given here. And one thing to note here actually is as the LF, ETLF will use cryogenics to cool the test masses, there will be these around 40-meter radius cryo shields around the test masses, which is a consideration then for the next topic, which is the topic of constraints then on the arm telescope and the signal recycling cavity design more broadly. So just to keep things simpler and more clear, this is the general system really that we'll be analyzing throughout the rest of these slides. So a single arm cavity 10 kilometers long, and then the signal recycling cavity with a Z-shaped telescope inside. And so, as I mentioned just a moment ago, as ETLF will use cryogenics, so these so that it has cryo shields of around 40 meters extended from the test masses. This effectively places a lower limit then on the SRC length for ETLF. But as we'll see later on, this isn't really too important of a consideration, as it turns out, for the design. For ETHF, on the other hand, we have a different picture really, and a more complicated picture. So some recent work from one of my colleagues, Philip Jones, whose paper is cited here, really tells us that we want to limit the SRC length for ETHF to ideally 100 meters or less to avoid degradations or significant degradations in the sensitivity at higher frequencies. So you can see, so these figures were just taken from the paper, and this first just shows the degradation in sensitivity compared to the initial ET design curve for various increased SRC lengths. And then the second plot here just gives associated correction options, essentially, of each of these traces, where to correct for these degradations, the ratio of the SRM to ITM transmissivities have been changed. And this has the unfortunate side effect of increasing the power on the central beam splitter. So this would be a problem for thermal lensing in the substrate. So you can see from the paper that I've cited here that they kind of come to the conclusion that around 100 meters or so for the SRC length would be a happy compromise here, really. So another constraint to consider, which is a little more loosely defined at this stage, is the beam size on the beam splitter. So here I just give kind of an approximate upper limit for what this could be for a given beam splitter radius to avoid clipping losses that are too large. And then for the minimum beam size, again, it's a little hand wavy at this point, but this is mostly important for ETHF as this will operate at higher levels of power, so inducing more thermal lensing, and this thermal lensing generally gets worse for a smaller beam size. But to cut a long story short here, really, given all these limits and constraints we have, we targeted a beam waist of 6 millimeters at the beam splitter with a stable SRC having a length of no greater than a few hundred meters. So now I'll go into some of the details of the varying arm telescope designs we analyzed for ETLF, and the HF analyses followed a similar recipe. So clearly the simplest beam expander you can have is just where both of your telescope mirrors are flat and you just have a lens at the ITM, which is responsible for changing the beam size between the beam splitter and arm cavities. So shown here is just the waist size and position of the beam propagated from the arm cavity as a function of the focal length of such a lens. And you can see to achieve a waist size of 6 millimeters, you really need an SRC then of exceeding 1 kilometer long. So we pretty quickly rejected this type of configuration for that reason. So then the next level of complexity is to allow curvatures on the 2 telescope mirrors. And this is already quite a bit more complicated now, as there are several degrees of freedom. But we can make a helpful assumption here to help out with this and reduce these this number of degrees of freedom. So as implied here, we can pretty much safely assume that the main Goi phase accumulation will come from the telescope to the signal recycling mirror, as the Goi phase changes faster close to the beam waist, remembering that we're targeting the beam waist at the beam splitter. So then
5 minutes, Samuel.
Okay, so then after some grid-based searches of the parameter space, we arrive at this plot shown here. And really the key takeaway here is that you can indeed achieve a stable SRC as indicated by the round-trip Goi phase here, but really only for quite a long SRC here, so around 250 meters or so on average from this plot. And it's also worth noting that if you want to go to shorter SRCs here, then the requirement then on the ZM1 radius of curvature is quite strict. So to alleviate these issues, we can again introduce a lens at the ITM to pre-shape the beam before it hits the telescope. And to skip over some of the details here, we effectively find that an ITM lens with a focal length of around 75 meters is pretty much optimal for this. And if we rerun the same kind of analysis, then again we see we can get a stable SRC again, but now with an SRC that's quite a bit shorter and also opening up a broader, a better range of ZM1 radii of curvature to reduce the strictness on this. So then, so from this plot, we can basically just select a given solution, and you can see in the last slide at the end a table of data which gives the exact optic values that we used. So now I'll just go into some of the just the details of the solutions for both ETLF and HF. So this slide just shows plots of the beam propagated through the SRC from the ITM to the SRM, and in both cases, the important thing to note here is that from the first telescope mirror to the signal recycling mirror, the beam is approximately collimated. And so this gives us quite a bit of freedom then in the design to further reduce the SRC length simply by just reducing this this distance from the first telescope mirror to the beam splitter. So you can see here from, even by reducing this from a nominal 70 meters to all the way down to 10 meters, we still have a stable SRC, and with a beam size on the beam splitter which is approximately of the target value. So the final aspect of the solutions that I want to discuss is just the sensitivity to any distortions in the optic curvatures. So this set of plots effectively show the mode mismatch from the arm cavity to the signal recycling cavity based on deviations in the radii of curvature of the telescope mirrors and the focal length of the ITM lens. And then, yeah, so it's quite obvious from these traces, this black trace, so the ITM lens focal length really is the critical parameter here in terms of creating mode mismatches with small distortions. So based on that and leading on from that, we just did an initial optimization analysis on the arm to signal recycling cavity mode matching based on the case where there's a thermal lens present in the ITM. So this thermal lens will alter the effective ITM lens focal length. So this plot shows the thermal lens strength in terms of the focal length of this lens, and then the y-axis here just shows the simultaneous change in the radii of curvature of both the telescope mirrors that are required to recover full mode matching back of the SRC to the arm cavity. I should note here that obviously this is kind of an initial analysis, and further investigations of the actual actuation strategy for the telescope mirrors would be required to see the other types of mode mismatch that you could correct. Okay, so in summary of all this, the larger beams present in ET and in third generation gravitational wave detectors more broadly mean that you'll have to have either a very large central beam splitter or more likely beam expanders in the interferometer arms. And so the design of these beam expanders and the recycling cavities is somewhat more complicated, also due to the fact that you want to limit the SRC length, especially for ETHF, to avoid this degradation in the high frequency part of the sensitivity curve. And to effectively limit this SRC length, you need a Z-shaped telescope, essentially with curved mirrors, and also ideally a lens at the ITM. And yeah, so you can also reduce the distance between the telescope and the SRM, assuming you have a collimated beam in that path, to further reduce the SRC length. And then finally, I showed that you can possibly correct for mode mismatches due to a thermal lens in the ITM with around, so using the most extreme thermal lens from this plot, with around 0.5 millidiopter change in the ZM radii of curvature. And that's all. So thank you for listening.
Thank you, Samuel. Very nice work. We have time for one quick question. If this is not the case, let's thank Samuel again, and we can proceed to the next speaker. Next speaker will be Jessica Steinlechner. Speak about R&D on coatings. Hi, hello, Jessica.
good. Can you see my screen?
Yes, very well.
Okay, great. Yeah, so I will give a brief overview of where we are with coatings for ET and a bit of background, which properties are actually relevant and how certain changes actually affect coating thermal noise. So just starting with a few basics about coatings. So the coatings I'm talking about are just the ITM and ETM coatings here. And coatings are made highly reflective by kind of building stacks of many, many layers. And we need two different materials at least, because the refractive index change at the interfaces between the layers causes the reflection. And we build up a certain interference pattern by selecting a certain thickness. And the ideal thickness to have as few layers as possible and as high reflectivity as possible would be a quarter of a wavelength in optical thickness per layer. So that means optical thickness, so the refractive index goes in, so higher refractive layers are thinner. And the higher our refractive index is, the fewer layers we need, and the thinner the layers we need are. And for the ETM reflectivity, with current LIGO and Virgo coatings, we would need about 38 layers to get the target reflectivity of the ETM and about half as many layers for the ITM. The reflectivity is actually not the main issue, so the technology is very good there. So the problem is actually that the materials we are selecting here need to have low coating thermal noise. I will go into a bit more detail on that soon. But we will also have low optical absorption, only a few parts per million, maybe even less, to avoid heating of the mirrors, to avoid thermal deformations and such things. And we need low optical scattering, and that means we need very defect-free coatings, and we don't want any microcrystals, so we need purely amorphous or purely single crystalline coatings, because microcrystals, which can get caused from heat treatment or from using non-ideal deposition procedures, can cause such scattering. So a bit more detail on the coating thermal noise. So this is a simplified equation describing coating thermal noise, and it's proportional to the square root of the temperature to the beam radius, as we've already heard in the previous talk, to the mechanical loss, which is a coating property or a material property, to the coating thickness. And there actually it's interesting to know that the refractive index of the material is relevant, but the thickness is mainly defined by the target reflectivity. And it is frequency dependent. So here with that frequency dependence, actually our reduced temperature for ET low F comes in. But the low temperature of ET low F requires a new substrate material due to high thermal noise of fused silica. So we are thinking about changing to most likely crystalline silicon. Crystalline silicon in turn has a low absorption at higher wavelengths than we are currently using. So 1064 nanometers are not suitable at all, because within the first few centimeters of the mirror, all the laser power would get absorbed. The telecommunication wavelengths is very a very promising wavelengths, or even higher wavelengths where some coating materials are lower absorbing are interesting. However, a longer wavelength also means a thicker coating, which then again affects our coating thermal noise. In either case, so ET low F and ET HF, we will need new coating material solutions. And when we are looking first at ETHF, so here we see our sensitivity plot, and we are interested now mainly here in the red curve, which is our coating thermal noise design. I've added in here in orange the coating thermal noise we would get with current advanced LIGO and advanced Virgo coatings. And we would be about a factor of 2 above what we need. So we are actually quite close now with the increased beam diameter according to the new design study. And this factor of 2 here is exactly what we are trying to actually achieve with the advanced LIGO Plus coatings. For advanced LIGO Plus, we currently have 2 candidate materials which would almost meet this goal within about 20% according to current status. And these are titania doped germania or titania doped silica to replace the tantala in the coating. The silica is fine, so the tantala has a high mechanical loss, much higher than the silica, and dominates coating thermal noise. But research here is not finished yet, so it still needs to be confirmed that the optical absorption can be low enough with one of these materials if the right deposition setup is used. It needs to get shown that a multi-layer coating shows a mechanical loss predicted from the single layers and such things. Virgo is looking also into silicon nitride as an alternative high index material that can have a higher refractive index, which makes the coating a bit thinner. So with that, this red line here, so that goal would be met. However, with silicon nitride, the absorption is also still quite high, and people are working on reducing it. There's also been a lot of work on silicon nitride in the past. Just to point out, so there are references everywhere under these underlined links if anyone is interested in more detail. So on silicon nitride, there has been a lot of work in the past in a LSC group in Taiwan, where they looked into how the silicon and nitrogen composition affects the refractive index. They looked into absorption and mechanical loss. And currently, Virgo groups are looking into absorption improvement of IBS silicon nitride and other properties. So clearly there's still a lot of work going on, but this research all looks very promising for reaching the ETHF goal. And one of the main challenges left is clearly the upscaling to about twice the size. But as Stuart already mentioned in his talk yesterday, currently in Scotland, they are working on setting up a large coating facility, for example, and there is also lots of development ongoing. So going to ET low F, an interesting thing is happening. So just to make clear here, so we are moving quite a lot to the left here on our frequency axis. And an interesting thing is happening when we are cooling the coatings, because the mechanical loss of silica and tantala gets quite a bit worse, so that we improve our coating thermal noise from cooling much less than expected. And it's even more interesting when we are looking here in pink and green at our silica germania or silicon nitride coatings, because the nice improvement we get at room temperature more or less disappears at low temperature. In case of silica and germania, the loss of both materials increases a lot. In case of silica and silicon nitride, we don't lose as much in coating thermal noise, as only the silica gets worse, but it more or less dominates the coating thermal noise, and improving the silicon nitride actually can't help us very much. So we need either a different material or at least much fewer silica layers to further improve the coating thermal noise here. An interesting option is, for example, silica and silicon, so amorphous silicon as a coating material, because it has a very high refractive index, which makes us need much fewer layers and a coating only about half as thick as a silica tantala coating. So in number of layers, even thinner in actual thickness. The best silica and silicon coating so far realized or actually predicted from single layer measurements would have around 8 ppm coating absorption, which is still too high, and even making this level reproducible requires further R&D, but coating research is going on there. Higher wavelength might also help. So this is actually one of the materials which are a very good motivation for going to wavelength around 2 microns. Also cooling the coatings. So my previous calculations were for 20 Kelvin. So going to 10 Kelvin gives us the dashed lines here. So we are getting much closer to our goal. However, at 10 Kelvin, we can tolerate even less absorption before we start heating up our cold mirrors. So that's even more challenging.
5 minutes, Jessica.
Okay, and another option to further improve coatings are, for example, nanolayers. Nanolayers means substructuring each layer made of even thinner layers. And nanolayers have been shown to suppress crystallization. They have also been shown to suppress the cryogenic loss peak in silica. It might make our silica better. But of course, adding in layers of a different material changes our refractive index and the whole coating design. Clearly, many other materials are also considered. So what I'm telling here is really just a few examples. And structural predictions, as Stuart also told about yesterday, give good ideas of which materials make sense to look at. And another option are multi-material coatings. So when we talk about multi-material coatings, we mean coatings made of more than 2 materials, which in principle is easily doable. It sometimes might not be so easy from a deposition perspective, but that's a different story. So what happens, for example, if we use our silica tantalum coating from before and add in one silicon layer here at the bottom, it almost sees no laser light. So our blue line here shows the laser light intensity, and that's more or less vanished here. So we don't have any significant absorption contribution, but we can make our coating thinner and need less layers on the top due to the high refractive index. So we win in coating thermal noise and can basically create a trade-off of coating thermal noise improvement. The higher the absorption is, we can or want to tolerate. So it's not really we can make both as good as possible, but we can balance between selecting some kind of ideal in-between solution. And here, of course, we are not really limited by which materials we combine. So this is a picture you also might have seen in previous talks this week. This presented measurements on silica doped hafnia, which looked very interesting as a material, and is actually looking into silica doped hafnia compared with amorphous silicon in the lower layers, with just 2 double layers of silica tantalum on top to reduce the absorption a bit. And this coating here can meet the ET low F coating thermal noise requirement at 10 Kelvin. And it had an absorption of 3.4 ppm per mirror, which according to the 2011 ET design study was within the target of below 5 ppm. More recently, the absorption requirement seems to get lower and lower. The question is, how low will it actually be? It might be as low as silica tantalum coatings currently, so just half a ppm or lower. It might be a bit higher. So I've just drawn here a few dependencies. That's by far not everything, but just to show what actually goes into defining the coating absorption. So it depends on how much substrate absorption we have, because it's about the whole total heat load. It goes in what laser wavelength we have, as it changes the absorption of coating and substrate. Very interesting is, of course, the heat extraction capability through the suspensions, but also the target temperature and just many other things. So defining actually a number for the coating absorption is not very easy and comes from many, many different sites within the detector configuration. So so that means we might not be at the end of the story for the ET low F coatings, and that's here one more option I would like to mention, crystalline coatings as an alternative coating concept. So with crystalline coatings such as AlGap or AlGas, coating thermal noise levels have been shown which are quite a bit below our requirements, so that looks very promising. However, Algas shows very low coating thermal noise and low optical absorption, but crystalline coatings need to be grown on lattice match substrates, which in the case of Algas is gallium arsenide, and that might very likely not be available in the sizes required for ET, while AlGaP has an advantage that it can be grown on silicon and therefore is very obviously available on in the same sizes as a silicon mirror. But AlGaP will need much more R&D on absorption reduction, because absorption levels shown so far were rather in the percent region. But using silicon as a substrate material gives the option for a variety of different materials which can be grown on silicon. Of course, also other carrier or growth materials might be options. And within ET Pathfinder, for example, there's quite a large work package concentrating on developing new crystalline materials that will happen at Leuven University. And we hope that we can test a few new interesting crystalline materials in ET Pathfinder. And also other options are around. So in Hamburg, we are looking into the option of a crystalline top layer on top of an amorphous coating to further reduce the absorption. In Glasgow, they are looking into ion implantation into the silicon to create some buried silica layers, which reduce the coating thickness. So there are a lot of interesting ideas around. And yeah, as I said, this here really was just a very short overview, and there would be much more to tell. So that's it from my side for now, and I'm happy to answer questions.
Thank you very much, Jessica. Very nice review. And yeah, this is actually one of the areas where a breakthrough can really bring real progress in the sensitivity of future detectors. And actually a lot of activity is going on right now for the advanced detector as well. Questions for Jessica?
I cannot raise my hand because I'm a co-host, but I could have a quick one.
Go on. Yes.
We were talking in the other sessions also about ET as an infrastructure that lasts a long time, where we want to improve, going down to facility limits. So we've seen from Stefan this nice curve where the facility limit is way below the current noise curve. But of course, to make use of that, we would have to improve all the other noise sources. So what's your kind of take on the long-term development in the coating world? Even if we get the first installation of ET to reach the target, how do we go beyond that? What would be the best way forward?
So you mean for HF, for example, or I mean, there's quite a bit of scope for actually improving the total noise by going further down with the coatings, or?
Yeah, for example, if we would ask you how to get another factor of 5, okay, noise improvement, is it a completely different approach? So it means coating improvement is never going to be enough, or could eventually, with more material research, slowly we actually get each year a little bit better? What just an educated guess, really.
So I think for ETHF, this will be much harder than for ET low F, I would think. I mean, for ET low F, you have really nice options like growing crystalline coatings, possibly directly on the silicon, or these kind of ion implantation ideas and similar. Also, probably we still have quite a bit less overview of potential materials which have low mechanical loss at low temperatures, while there has been really a lot of work into looking into different high temperature, so room temperature materials over the past years. And there it already turned out, I mean, over the past 10-15 years, that it's quite hard to further improve coating thermal noise. I mean, clearly current materials people are looking at might have scope for going a bit below this factor of 2 improvement. I don't really see a factor of 5 here. But I mean, there might also be possible crystalline solutions for room temperature if we can grow them big enough and the technologies for the substrate transfer make enough progress.
Yeah, sounds good. No, I think that sounds very interesting. So crystalline first, and then we'll see how we get, you know, maybe even into HF with that. Okay, yeah, sounds good.
Any more questions for Jessica? Okay, if not, let's thank Jessica again. I see a comment in the chat window from Stuart. Stuart, do you want to comment yourself? No, so no, okay, I see. So I'm going to read the chat. The ultimate goal for coating optical mechanical loss would be to reach close to bulk-like properties. That doesn't mean another factor of 5 is easy, but there is no physical reason why it can be achieved. So an optimistic overlook. Thank you for your comment. So let's proceed with the last speaker of the morning, Ursula Gibson. She's going to talk about the development of crystalline silicon suspension structures, which is another hot topic, which already came up yesterday during the session in the afternoon. We see your slides. You can start whenever you're ready.
Wonderful, thank you. First off, thank you very much for letting me speak to you. This is a community that I really just encountered for the first time about a year ago when Flavio Travasso came to me at a conference and said, hey, can you do this? So I hope that you will tolerate my naivete, but I think that some of the things that we've been doing, trying to make crystalline silicon fibers for totally different applications, are actually going to be of interest to you here. And I want to acknowledge John Bellotto and Wade Hawkins at Clemson University, because they are the ones that make the highest quality material that we've been studying. So my understanding of what you need is that really a crystal suspension is needed, single crystal and silicon, so that you can have no boundary thermal resistance at the bottom end primarily. So you need single crystal, you need high purity material, smooth surfaces, low number of defects, and perhaps you haven't worried about it much, but stress can be an issue when you're making thin crystalline materials. And what we do, which I'll tell you in a second how we do it, is that typically as we make the fibers initially, they are polycrystalline. They do have some stress, but they have incredibly smooth surfaces, and they're really quite easy to work with. We can improve them by making interface coatings. Some of these lead to higher crystallinity. They reduce stress. And a key factor of what we have been working on is the use of laser annealing. This allows us to taper the fibers. It allows us to recrystallize them. It allows us to do some really interesting material science things. And in addition, one of the things that we found is hugely useful is to use not just pure silicon, but to add an alloying element. So if you think that you want to make yourself a nice thin fiber, there are sort of three largely encountered techniques. One is you put it in a crucible, you put a seed in contact with it, you pull it down. Another one is that you have a polycrystalline material here, you apply heat and you put a seed in contact with the top and you draw it upwards. And what we're doing is very different. We start with a large chunk of glass, which has a hole drilled into it. We put an interface coating if we desire to use one, and then we just load the materials. We then put this onto a conventional drawing tower, the type that's used for making optical fibers, but it can also make very large diameter materials. And when we put the silica preform into the heat zone, the semiconductor that we have put into the middle just melts, and then the silica acts as essentially a crucible that shapes the fiber coming out. And so we get a nice cylindrical product. So we can do this, and as I said, we have been targeting primarily infrared optical applications, although we've extended to terahertz now, which has moved us out into the larger core diameters. And this is what we have done so far. I think that it's not entirely trivial to do large core silicon, but I don't think it's impossible. The learning curve, this whole area is about 5 years old in terms of using an interface coating, and it's a rapidly expanding field. So we're young, but we're learning fast. So I said that the silica acts to form the fiber. It can also be used after the fact as a vessel for tapering and recrystallization of the core. This is an example which is on a very small scale because our collaborators in England are interested in the nonlinear optical properties of the core. And so they wanted as small as possible to get the highest intensity of light. But you can see that the glass can be used essentially to manipulate the core that you have, and you can get different shapes inside. Down below is an example. This is actually a silicon germanium alloy, and so there are some slight sort of mottling effects due to the way that those two materials segregate out when you first form them. But you can see that the material as drawn essentially is a rod which has a silica coating, and then inside is the semiconductor material of interest. Now, I said that as drawn, they may be inhomogeneous, and they may have quite a lot of strain. And so what we have done very successfully is that we take our fiber, or the glass people call it a cane because it's rigid, and we run that past a CO2 laser, and we can actually melt the core. We can watch as this occurs just by using a CCD camera, and we can learn a lot about what is going on in terms of making the core homogeneous, recrystallizing it, etc. And this is not relevant to your applications, except that it shows that when you're working with pure silicon, going fast is a better annealing process than going slow. And that's because whenever you try to recrystallize this material, you're always dealing with a competition between nucleation of new grains and growth of the one that you want. So just to convince you that this process can actually be successful, I show here some, this is actually, yeah, this is silicon fiber. And this is as drawn, and you can see that the X-ray diffraction peaks are numerous and quite broad. And after annealing, although we still have a large number of them, they have clearly sharpened up to essentially the resolution of the instrument. This is a slightly unusual presentation of X-ray data. These are not the Bragg peaks. This is actually, if you have a single fiber, you tune to one Bragg reflection and you rotate the fiber. This allows you to tell whether they are single crystals or not. So small numbers of peaks, or correlations of the peaks, allows us to determine really what's going on. So I'm going to take you back to the interface coatings, because that is actually something that affects the crystallinity of the core as well. The very earliest silicon draws, just with silicon in a silica glass cladding, the cladding cracked. There was a large amount of oxygen inclusion, and essentially things kind of quieted out for a while. But we found that the heating cycle that's used, or the introduction of an interface layer between the silica glass and the silicon core, does a huge job of reducing stress, and it also blocks oxygen transport into the core. This, for our purposes of optical transmission, has made a huge difference, but I expect that all sorts of other properties go along with the optical properties. And this is a recent result using a different coating. And what you can see that even as drawn, there are very few Bragg peaks. And if you look at the rotational scan of this material, what you find is that it is a single crystal. And we have even found that different coatings can influence what orientation is preferred along the axis of the fiber. So interface coatings can help, but there's another area where we find huge improvements in materials. And that is if we add an additional element, we can lower the processing temperature, which is advantageous because then the silica, which has been essentially turned into a crucible for our purposes, is not affected as strongly. And what we find is that this is an image actually of the annealing process, and this is the intensity. And you can see there's a difference in the emissivity of the molten material and the solid. So we can actually watch as we recrystallize. Doing this, we were able to create single crystals along the entire length of the that we annealed. Okay, so this isn't maybe what you guys care about, but it's a first step. And I wanted to just show you the data from Flavio, who measured, and unfortunately, when you put an alloying element in there, your thermal conductivity drops quite a lot. So instead of having something that we're going to leave inside the material, I started thinking about what if you actually can remove that? And based on our prior experience with a combination of semiconductors, what we found is that we start
5 minutes, Ursula.
Okay, thank you. We start out with a combination of the two materials in a complicated structure. When we heat with the CO2 laser, we draw together the lower melting point material. We can translate this melt zone through the material and leave behind single crystal silicon. And very little of the gallium antimonide is left behind. So gallium antimonide is a little complicated because it leaves all sorts of carriers behind. So we moved to looking at gold silicon eutectic. And this is some work that we are doing where we're interested in terahertz transmission. So this is a large core fiber. And the take-home lesson here is this is TEM, showing that we have single crystal material. There is a tiny little secondary crystal in this sample right at the end of the translation region. But what we see is that the properties, the transmission properties, both in the terahertz and in the infrared, are essentially the same as high resistivity float zone silicon, which is kind of the gold standard for what you can do in terms of silicon. And there's a little bit of oxygen incorporation as shown by the absorption out here at 9 microns, but it looks very promising. So where to go with this? Number one, longer single crystals. So far, the bulk of the work that we have done has been where we make a mixture and then we pull out the undesired component. That doesn't let you get a meter fiber, but recently what we have found is that we can actually take a fiber that is pure silicon, introduce a small region of an alloying element, draw that through and leave behind crystalline high quality material. We can do that with different eutectic systems. Gold is one, but we can use other ones that allow us to really control the temperature at which this processing occurs. I also wanted to point this out. I added this last night because I thought it could be of interest. In this case, what I have done is I have taken one of these glass-coated fibers, polished away half the glass, placed it onto a silicon wafer, and then I've used a CO2 laser to actually weld the two, and they are crystallographically connected. There is no evidence of the alloying element that I used in there to encourage the welding. With larger cores, we do have to concern ourselves about stress management, but interface coating, again, we're seeing huge strides in the effects of different materials there. We can change the glass composition. And one thing which I thought might be of interest, because when I was reading your literature, I saw that rectangular ribbons are a possible solution. They don't have to be cylindrical. And I wanted to point out that there's no reason that silicon can't at least adopt a somewhat different form. It doesn't have to be cylindrical. The crystal orientation will affect the thermal conductivity, and we've had a little bit of success using seeds for regrowth when we draw the second material through the core. And if it were desirable, we could leave some of the metal in the core right at the end so that you could use that as a thermal connection up at the top, for example. My ignorance is leaping to the fore here. One thing that I did want to bring up, just in case it's of interest, is whether the use of isotopically pure silicon would be a good idea. So this is the thermal conductivity of silicon for different quality of material. So if you take natural silicon, sort of as clean as you can get it, this is the thermal conductivity curve as a function of temperature. And the peak is right around the temperature where I understand you may be operating. But what really struck me here is that if you use isotopically pure silicon, you can get a huge increase in the thermal conductivity. Again, maybe you guys have been on this for 10 years, but for me, this was pretty cool. So in summary, this glass-clad semiconductor fiber is actually, I think, a promising way to start making materials. We get very high quality surfaces. This tapering kind of scheme can let you fabricate terminal cones. There's a lot of work in the optical community for increasing the purity and improving the crystallization. And we have an incredible processing flexibility, I believe, with the use of eutectics. And so really, I think that's about all I have to say, except that, I'm excited that there may be an additional use for the technology we're developing. Thank you.
Thank you. Thank you very much. Very, very interesting talk. There is one question in the chat from Eric. Are higher cross-section aspect ratios greater than 2 possible as well?
Okay, so the only thing that I know about making not cylindrical material really is this one paper by Bellado's group. And we have not tried to make an aspect ratio of anything other than 1. But I am very optimistic that we can do this. I think that an aspect ratio of 2 to 3 should be doable. 4 is possible. There are some instabilities that may arise if you have the liquid in a very thin cavity. But I think that that's an interesting area that we can explore. Again, the silica glass does the containment. It drives the process. So possibly with the use of an alloying element to lower the melting point of the silicon, we can make our crucible a little bit more rigid and we can get improved control. So I think it's totally possible.
Thank you. Leonard, please go ahead.
Yes, thank you. I was just interested in how about hollow silicon fibers? Do you deem that to be possible to manufacture at all?
Okay, if I were going to make a hollow silicon fiber, I think I do think it's possible in a couple of different ways. One thing you could try to do is to put something into your preform that would get dragged down along with the fiber, and then that would be sacrificial. You could etch it away later. It's a little tricky to really know whether we could just put a rod of SiO2 down the middle and have that follow down the fiber. I think that would be unstable. But one of the things that's really interesting is if you put an additional element into your core, and you do the right thermal treatment, you can get that additional element to concentrate in the middle of the fiber. And there, again, you can do a sacrificial etch removal of that material. That will be a slow process because you don't have very good access to the core. But if you're patient, perhaps you can do it that way too.
All right, thank you.
Oh, and one other thing, it just occurred to me. If you put a hollow silica tube into the silicon melt and you pressurized it, that might give you directly an annular silicon structure.
Yeah, I have a question. Maybe you said I missed it, but this glass clad that you put outside the fiber can be removed, is left on the fiber, produces fiber. So it can be removed without leaving contaminants?
Yeah.
Okay, so it's...
Yeah, there's very good segregation of the silicon. Flavio did a little bit of that work when he was looking at the thermal conductivity of some of our early fibers. And I think that etch removal of the silica glass will leave you very clean silicon.
Okay, but I don't understand how it is possible to see it with the thermal conductivity. This can be seen by thermoelastic noise because you... Okay, so it was checked with thermoelastic noise, not with the thermal conductivity.
Yeah, so this is where my ignorance comes to the fore. You know, thermoelastic noise is a phrase that I encountered just a few weeks ago. So,
okay.
There are two more comments in the chat. I'll read the comment from Eric. What is more difficult, which is again about the aspect ratio of the fibers, which is more difficult, making a monocrystalline fiber of 0.5 millimeters or 3 millimeters?
I'm sorry, what is it? It's harder to do which?
Circular, yeah.
Oh, okay. Circular is what Mother Nature prefers. But whether we can make ribbons, and you know, if there were a really strong desire to make ribbons, I believe we can learn to do that. Just based on the fact that this simple trial of trying to make a square came out kind of square, and they were not pushing the technology. I really think that if we want square silicon or rectangular silicon, we can do that. It will have rounded edges. It will not be nice rectangular.
But maybe
my question was, is it more difficult to make it thicker than a thinner one? 0.5 millimeter or 3 millimeter? What is the most difficult?
Thicker. Okay, so there's a lot we don't know. My feeling is that if we go to ribbons, we may be able to make material that has one larger dimension. When we go with cylindrical materials, bigger is harder using our technique because the silicon expands like 10% when it freezes. And if it's a big chunk of silicon inside a big chunk of glass, that freezing process can be destructive. That's where the interface coatings come in, and also some other things that we've been doing lately.
Thank you.
I'll read one last question from Stuart. Is there an expected limit in the purity of silicon fibers compared to bulk silicon?
Is there an expected limit in the
purity?
In the purity. Yes, there's an expected limitation. I don't think that we can make fibers that have fewer than maybe 10 to the 16th impurities per cubic centimeter. That's pretty clean. I mean, the results that we had on the terahertz and the infrared transmission have really made me very enthusiastic about the quality of the purity. The other thing is that we found that this business of drawing a metal through the core, that is actually a zone refinement technique that is known to the silicon industry. And these fibers are sort of the perfect geometry for that. And so if we need to, I think we can do a multiple pass refinement and get the purity very, very high.
Thank you. So let's thank Ursula again. This was a very, very interesting talk and clearly a hot topic for the community. I would like to thank all the other speakers of the morning. The session will reconvene this afternoon at 3 o'clock, and the focus will be on seismic and Newtonian noise and cryogenics and vacuum.